Okay, so this is the misconceptions of matter activity. We're going to start here with station 1. Is air matter? So we're first going to take the mass of an empty balloon, 2.7 grams. So go ahead and put that in your data chart. The reason we have the tape on there is so that the balloon doesn't fly away in a hot second. Miss Baker's going to blow it up, and she's going to put it back on there. And now we find the mass of the inflated balloon is 2.8 grams. So the question is does air have matter? So use your fancy math skills, do a little subtraction there to determine the mass of the air. And I think based on that, you can go ahead and answer the questions.
Remember, with your definition, air has to be matter if it occupies space, so it takes up a volume, and it has mass. So take a look at that data again and see what you think. In our next station, the temperature and volume, we are going to be looking to see if the temperature will actually change the shape of the balloon. So in your first two pictures, you can see here in the red balloon as well as the green balloon you're going to see next, we have a balloon that is filling the entire beaker. So do you see how that fills all the way to the very, very top? And then when we place the red balloon in a heated water bath, the green balloon is also going to be inserted into ice. So here is our balloon on ice. The balloon, as you can see, was also placed in the freezer. So after a short while later, you're going to notice that the balloon has changed shape. So in your chart, you're going to be drawing what the balloon looks like. The red balloon was actually placed in hot water, and then we boiled that water at the same time. After quite some time later, you can see that the balloon has actually changed shape. So this is what you are going to draw for your next picture.
Okay, so now we're at station 3, mass of ice and water. So have you ever wondered if the mass of the ice when it is frozen as ice is the same, less than, or equal to the mass of the liquid when it is a liquid? The water when it's a liquid. So we're going to take the mass of the frozen ice first in this little film canister. Just got it out of the freezer. Take note of that. It is 15.2. So Miss Baker has been moving those particles, increasing their kinetic energy, trying to get it to melt. And now I think it's ready to go. So she's going to put it back on the balance. And what do we find? 15.2. Interesting. The before and the after are both the same. So that means that when the water molecules were frozen as ice and when they were liquid water, they're both the same mass. All right, we are back now with station number 4, the mass of dissolved sugar. So we're measuring out the mass here, 5 grams of sugar. And we're going to try to add it to some water here and see if the mass changes as you add it to water, as it dissolves in water. Okay, so we have that measured out to 5 grams of water. And our mass of the water in the beaker is
281.4.
Okay, so now we're going to add the sugar to the water. Make sure you get all those molecules off that stirring rod, Miss Baker, before we mass it.
Sure, we're good. So we're stirring just to help assist with that process of the sugar dissolving.
What are some things that we could do if you wanted to increase that a little bit, speed that up a little?
Wonder if I could stir faster?
Maybe.
Will that work? What if I heated it up?
Definitely.
There we go, there we go, there we go. All right, what do you think? Does it look pretty dissolved?
Pretty dissolved, but though I see some, wow, I see some sugar molecules on that stirring rod. Oh my goodness gracious. All right, let's do it. And after all that stirring, the mass now of the sugar added to the water in the beaker is now 286.4. So you tell me, did the mass of the sugar or the mass of the water change when you dissolved it inside of your beaker? So here's a beaker filled all the way to the top with water. The question is, how many cotton balls can you fit in this cup until it overflows? So we agree that water has mass and volume. So therefore water is matter. And I think that you could probably agree that this cotton ball right here, I guess I'll put it over there, also has mass and volume. It takes up space, and if you put it on a balance, then it would also have a mass. So how many of these cotton balls can you fit in this beaker without it overflowing, considering that it does have mass and volume? So I'm just going to start adding them here. 1, 2, 3, 4, 5, 6, 7, 8, 9,
16, 17, 18, 19, 20, 21, 22, 23. So I think you get the drift here.
I don't want to keep you all day, but you get the drift. It's interesting that if both of these things have mass and take up volume, then the water is filled to the brim. It's interesting that it continues to accept cotton balls. So think about that. Think about why that happens, and let me know if you have any questions. So here I've got 25 milliliters of rubbing alcohol and 25 milliliters of water. I'm going to add these substances together and determine how much volume I have total. So the first thing I'm going to do is I'm going to pour in the 25 milliliters of rubbing alcohol, and then I'm going to pour in the 25 milliliters of water. After I do that, I'm then going to look to see how much of each substance I have. Okay, so if you look here, it's a little blurry. Come on. There we go. 25 milliliters of rubbing alcohol and 25 milliliters of water, and it looks like I have 47 milliliters total. But I thought 25 plus 25 was 50. Think about that. Okay, so here we are at station number 7. The mass of the steel wool before we do anything is 10.8 grams. Okay, so now we're going to take the mass after Miss Baker lights the sucker on fire. So we're going to make some observations after she lights it on fire, and then we're going to take the mass. So I'm going to turn the lights off so you can really see some action here. Where's the light switch? So as she's doing this, make some observations. What do you see happening? She's going to try to make sure that she gets it in every possible spot. She spread out the steel wool so she can get it, try to get it hot on every spot. Watch your fingers there, Miss Baker.
Whew, good thing I got a nice
It
wire
be smoking
glove.
up in her. I'm smelling some things, guys. Ooh. Okay, what do you think? Can we turn the lights on?
I think we're good.
Okay. So, based on your observations, we've got one more to make. So, you can see at the top where she's holding it, if she moved her finger out of the way a little bit, it's maybe a little bit of a darker color underneath where her glove was compared to the other spots. If you look here, you know, put it on this and see if we can, with the background, it's a little bit better.
Right here you can see.
Oh yeah, right there. At the top, notice that. Does it the same color or is it a different color? Down here at the bottom, different color. Okay? So, I want you to make some predictions. Do you think it's going to be greater than, less than, or equal to 10.8? Greater than, less than, or equal to 10.8 based on your observations that you saw. Okay, so we just put it back onto the balance, and notice now that after it's 14.4, what? 14.4. Who said that it was going to be greater than? Why do you suppose that is? Think about what you saw. We saw a color change. What does a color change indicate? Indicates that there's been a chemical reaction that has taken place. So what's your change there? Do your subtraction or addition or whatever the heck that is.
14.
Think about steel wool. Steel is made of iron. What happens to your bike when you leave it outside too long? What do we call that? Iron oxidation is the fancy name. It's for a chemical reaction that takes place. So tell me where you think that extra 3.6 grams of matter came from. It's not a mistake, it's legit.